Welcome everybody and Unit 5 series of IB Chemistry. Today we will let's start with section 5.9, which is pre-equilibrium approximation. We're going to write the rate law for the reaction. But if we look at the rate, like in here, we usually use this law step, which is really good. So I have to write the rate law like as a normal person. We have K2, which is the rate constant reactants NOBr2 and the NO. And now you feel like happy and you're done because this is the slow step and we wrote the rate law. But you have to keep in mind something. Whoops, we have a problem. We have NOBr2 in here and NOBr2 here. And the NOBRs are intermediates. Okay, these are intermediates. So what's the meaning of having intermediate? You have to keep in mind that you have no control on the intermediate. You have no control on their concentration. And that's why I have to present the intermediate concentrations in terms of something that I can control. You have a beautiful thing in step number one, which is this. You just notice that you have reversible errors. And reversible errors mean that you have an equilibrium. Okay, all right, so the equilibrium means that the rate of the forward reaction is the same as the backward reaction. Okay, so what does it mean? Okay, since we're dealing with rates, then I have to write the rate for the forward reactions for the first step, which is equal to rate is equal to K1. I put K1 and then open the bracket and just put the reactants of the forward reactions, which is an O in addition to Br2. So this rate of the forward reaction is going to be the same as the rate of the backward reaction. How can I write it? The backward reaction is like that. So you have to put K. What we call K, it's -1, and you just open bracket. This is your reactant at that point, which is NOBr2. Perfect. So you have this beautiful relationship that is highlighted in yellow. Now, how can I get use of this? As we said, let's go back again to our original equations of the slow step, because like the rate determining step, which is the slow step, is our key to write the rate law. So this was our problem. How can I get rid of the NOBr2? We can get rid of this magnitude in terms of this helpful equilibrium thing. The rate of the forward reaction is the same as the rate of the backward reaction. So if I want to take this concentration, which is the troublemaker guy, and just want to represent it in terms of the other thing, what should I do? You have to say, I need to divide over k-1, and this is k-1. We can cancel the case, and that's why we can represent the NOBr2, which is the troublemaker, in terms of the other concentrations in here. So it's going to be K1, NO, and Br2, okay, over k-1. So instead of writing NOBr, which is the troublemaker in here, I have to say, okay, it equals to this magnitude in here. So I will take this magnitude and just like substitute it instead of the NOBr2. Guys highlighted in green, we're going to write them instead of NOBr. But we have to write like the K2. It's like the same thing, K2. And we open a bracket. We have to put the guys in here that represent the NOBr2. It's K1, NO, and Br2, all right, over K, skip this here, -1. Okay, and then we have to put this as it is, like the NO as it is. And then if you just make some rearrangements of the thing, you can notice that you have NO here and NO here, and then it becomes the NO squared, and the Br2 remains as it is, like not changing anything in it. And you just notice that we have k-1 and K1 and K2. So we can say this is K2 and K1 over k-1. And we can hopefully represent all of these k's in terms of another k, which is KOBS, which means K observed. And then we can write it like NO to the power 2 and then PR2, as we can see. So this is the rate law for your reactions using the pre-equilibrium approximation. The approximation means you have to look at the equilibrium reaction and then just do a substitution thing in say in terms of having an intermediate. Let's take another example. This is another one. Okay. The question says, how can I write the rate law for this equation? So first of all, you have to look at which of these is the slowest one. This is the slowest one. So generally, you have to say the rate is equal to K2 times N2O2 and then BR2. Perfect. But we have a disaster at the point, right? We have N2O2 and we have N2O2, and this is as intermediate. And according to this case, we shouldn't have an intermediate in our rate law. How can I get rid of this magnitude and in terms of substituting things? Thankfully, we have the reversible reaction. And reversible reaction means the rate of the forward will be the same as the rate of the backward reactions. So if you want to write the forward reactions law, is going to be the K1, okay, NO, you have two NOs in here, which means it's going to be NO to the power 2. And it's the same as K negative 1, okay, and N2O2. Perfect. And since we don't like to see the NO2 in our experiment, I have to get rid of this magnitude. So we have to divide this over K negative 1 and K negative 1. We can cancel the K's, and then we got N2O2 is equal to K1 over K negative 1 multiplied by NO to the power 2. So this magnitude that will be highlighted in the red will be substituted instead of this guy in here. So how can I do this process? We just put K2. I'm sorry for writing K like ours, but I just like my method of writing it. And we multiply by K1. You just open a bracket. You can put the guys in here like the K1 over the K negative 1 and then NO to the power 2. And then we just put this as it is, which is the square bracket of BR2. All right. Now, we have to make some rearrangements. We put the K's together in terms of the KOBS, and then we write like NO to the power 2 and then BR2.